Okay. I'm just gonna get started. That's just because there isn't time for it. If you look at the schedule, we're gonna finish chapter 23. You'll have an SI class on Thursday next week. But you won't have had a week since I finished chapter 23, so I'm just doing it online. And also because I had an online version of the quiz, because often it ends up the test is immediately after I finish chapter 23, so I wanted to schedule that. So you will have an SI. You won't have an SI after a little later when we would have had chapter 15. So chapter 15's quiz will also be online. David will let you know when he's going to be out, I believe, but he's going to be out on let me not I think it will, I have to look at the schedule. But so we will have you will have an SI this week, but there's not going to be a quiz in it. Because I already have an online quiz. The week after spring break, David will be out. Then you'll have the online quiz for chapter 15. See, we do have a quiz this week. Next week, you don't have a quiz. So you have a quiz today. Yeah, let me just. So I will go through the announcements and explain the schedule. So no, right? Yeah. No. Isabel, sorry. Sorry about that. Chapter 22 quiz. Sorry, the chapter 22 homework due tonight. Chapter 22 quiz will be today in SI. The chapter 23 homework will be due on the 24th. That is Tuesday next week. The chapter 23 quiz. Sorry, that's Tuesday. Not next week, the week after. And the chapter 23 quiz, because of scheduling issues, will be online. Chapter 23 quiz will be on Blackboard from Tuesday the 17th, when we will finish chapter 23 through to Tuesday the 24th. You'll have a week to do it. It'll be online. It's timed. So you have one sitting of 40 minutes to do it, but it's only the same night. It's only like 25 questions, mostly multiple choice. I doubt it will take that long. You get one attempt, but make sure you have a 40-minute block of time to do it. You can do it at any time during that week, but you get one shot. And the short answer questions on it have to be graded manually, so you may not immediately get your grade back, because I got to go through and read them. And I believe the way that's going to work is just you're not going to see your grade until I've finished grading. And then on the 24th, Tuesday the 24th, that's not next week, it's the week after. That will be our exam on chapters 1 and 21 through 23. And that will cover that material. And yeah. Oh, and next week we're not going to have the lab will just be for makeup because we're ahead of schedule on labs. So let's continue on talking about weathering. Chemical weathering is the effects of temperature and moisture. And so chemical weathering, which is weathering, caused by chemical reactions, is most rapid in areas with high temperatures and abundant moisture. So wet areas in the tropics, that's where you're going to see the most chemical weather. In very cold areas, polar regions, and very dry areas, deserts, chemical weathering is relatively sluggish because you need both water, because mostly this is interactions with water, and heat, because chemical reactions go faster when it's hotter. So if it's cold or dry, you don't get as much chemical weather. So here's a short video about chemical weather.
The second kind of weathering is called chemical weathering. Chemical weathering causes changes in the rocks from the reaction of different chemicals on the surface of the rocks. One common example of chemical weathering is called oxidation. If we were to leave an iron nail in a cup of water for a few weeks, a chemical change takes place. The nail gradually becomes coated with a dark red substance we call rust. Rust is oxidized iron. Here we see the difference between a shiny new nail and an oxidized nail. This rusting or oxidation deteriorates any surface on which it reacts and will eventually cause it to break down and fall apart. The mineral iron is present in many different kinds of rocks, and oxidation can break down these rocks if they're exposed to water for long periods of time. But are there other ways in which rocks can chemically weather? These rocks are covered with a plant called lichen. They illustrate another example of how the chemical weathering process takes place. The lichen actually secrete a mild acid which can dissolve or eat away the surface of the rock. Carbonic acid, a mild corrosive agent, can form when water and carbon dioxide combine naturally in the air or below the earth. Underground caverns like this are one of the most spectacular examples of the effects of weathering caused by carbonic acid. This cavern started out as small openings below the Earth's surface where water seeped in. The water combined with carbon dioxide from decaying plant material in the soil to form carbonic acid. As this acid dissolved the rock around it, the pockets gradually grew in size. The force of gravity, combined with underground streams, carried the dissolved rock fragments away until finally a huge cavern was formed. This, along with the continuous seeping water, caused the cavern formations to grow even stranger as time passed.
So certain rocks and materials are more resistant to chemical weather. Because certain minerals are more easily, more reactive and more likely to break down than others. So the effects of modern chemical weathering can be readily observed by looking at cemetery headstones, because cemetery headstones come in a few different types of rock, and they're exposed to the elements. Marble is composed of the same mineral as limestone, calcite, and therefore it readily reacts with slightly acidic rainwater. It weathers very easily. While granite, on the other hand, is primarily composed of silicates, which are much more resistant to weathering. So a granite headstone is more resistant to chemical weathering than a marble headstone. So here's sort of a summary of weathering. You can either have mechanical disintegration, where things break into smaller pieces without changing its chemical makeup, or chemical decomposition, where the chemical composition of rocks changes. So mechanical weathering, you can have things like frost wedging, which is freezing and thawing water in cracks, salt crystal growth, which is the salt crystals growing from evaporated salty water, can also wedge cracks open. Mechanical exfoliation, rocks expanding and cracking as overlying rocks are removed due to erosion. So when pressure is released, sometimes rocks will get bigger and they'll break apart in that process. Root penetration, powerful tree roots grow in rock fractures. Thermal expansion and contraction can have effects, where enlargement and reduction of the crystal structure in response to heating and cooling. So one of the effects here is sometimes when rocks cool after igneous rocks cool after they form, they shrink, and sometimes this causes them to break apart. One of the most dramatic versions of this is these basalt pillars that form like hexagons. Can be seen in things like giant staircase and places like this. And then abrasion, rocks and minerals collide in a moving current of water or wind. Now, chemical weathering is where the chemical properties of the rock change. You could have dissolution, soluble compounds such as limestone get dissolved. This produces caves. Oxidation. Mineral ions combine with oxygen to form an oxide. This is very common with iron and produces rust. When iron rusts, it tends to get larger, which causes things to break apart. But other metals will also oxidize, like copper oxidizes and other things oxidize. You don't see it so often with certain stuff like aluminum or things, because aluminum actually oxidizes so fast that the process doesn't proceed very far. And in the ground, it's always pretty much always oxidized. And then hydrolysis, where H+ ions displace other ions to form a different mineral. This is common with feldspars, which turns feldspars into clay minerals. So that's how clay gets formed. Feldspar gets chemically weathered to form the clay minerals by this process of H+ ions replacing other ions. Now, once something has been weathered, broken into pieces, it then can move to somewhere else. That process is known as erosion. This is the downslope movement of soil and rock due to gravity and other various geologic agents. The most common agents for erosion include just gravity, stuff rolling down the hill. That's called mass wasting. But the primary carriers are things like streams, glaciers, wind, and waves. Those are the main things that move sediment around. So here is a short video about water and wind erosion.
The landscape of Earth has been formed over millions of years, and it is constantly changing. Some changes are major events that you can see happening, like volcanic eruptions and earthquakes. Other changes to Earth's surface are happening so slowly that you cannot notice them from day to day. One such process is erosion. Erosion happens when rock or land changes shape over time. There are different types of erosion. One type is wind erosion. You may not think that wind can change the shape of Earth, but this has happened in many places. One location that has been shaped by wind erosion is in the southwest United States in Arizona and Utah. This area is known as the wave because it looks like an ocean wave crashing. But how did it get this shape? Wind blowing through the desert carries sand along with it and blows across the rock. This wears away small amounts of the softer rock, and over a long enough time period, the wind creates unusual shapes in the rocks. This area of Utah, called Monument Valley, has some of these unusual rock formations caused by wind erosion. As the rock has been worn away, it has left behind tall structures like these totem-shaped rock pillars. Wind erosion is common in areas of land that are higher in elevation, such as these formations, also in Utah. Another common type of erosion is water erosion. This occurs when water causes rock or land to change shape over time. One of the most dramatic examples of water erosion is also found in the United States. The Colorado River flows from Colorado to Mexico. Over millions of years, the water traveling this path created a canyon. This canyon is now called the Grand Canyon and is a well-known tourist attraction. The canyon is a mile deep and up to 18 miles across at its widest areas. This amazing sight was shaped entirely by the water running over it day after day. Another amazing example of water erosion can be seen along the coast of Scotland, where you will find a rock formation known as the Old Man of Hoy. In the same way that river water can erode rock, ocean waves hitting the land again and again can also cause erosion. This particular formation is called a sea stack. It is a large column of rock that is left after wind and waves erode the surrounding rock and cause sections of the cliff to completely collapse. The Old Man of Hoy is almost 450 feet high. You can figure out if erosion is caused by water or by wind in a simple way. If there is a water source there, like a river, a waterfall, or an ocean, then the erosion is due to water. There are beautiful examples of wind and water erosion all over the world. Many of these locations are popular tourist destinations, while others are rarely seen. Maybe someday you will see one of these wonders for yourself.
So let's start talking about erosion. Water erosion is the most common type of erosion, so we'll start by talking about that. So we'll start by discussing runoff. If rainfall exceeds the amount of water that can be absorbed into the ground, the excess water has to go somewhere, so it runs off across the surface. That's runoff. And as this water flows over the surface of the ground, it can be particularly erosive in areas like a freshly plowed field without any vegetation to hold the soil in place. So places where the ground doesn't have ways to resist being the particles getting picked up and carried off. So vegetation is very good for holding the ground in place. You can also ensure that the ground is better at absorbing water. Cities are particularly bad with this because we've covered all our surfaces with impenetrable materials, so that all the water turns into runoff. So runoff usually occurs only over short distances before it either soaks into the ground or empties into a stream. But yeah, if you pave an area, all that water is not going into the ground, it's going somewhere else, and so you can end up with a lot of water, right, hitting the first bit of soil, and you get potentially a lot of erosion. So any channelized flow of water between two well-defined banks is a stream. And to a geologist, the size does not matter. A small mountain brook and the Mississippi River are both streams. It's a general term. And as a stream flows, that stream will carry with it other material. And this material is called the stream load. And in general, the bigger and faster a stream moves, the more it can carry. And the load of a stream will vary from dissolved material to fine particles to large rocks. And the stream load at any given location or time depends on several factors like the stream's gradient, the stream's volume, its current velocity, and what the channel is made of, the material of the channel. And we can divide the stream's load into three components, depending on how the material is carried by the stream. Those three components are material just dissolved in the water, the dissolved load. The dissolved load will stay dissolved in the water until the water evaporates. Then there is material that's suspended in the water. This is like silt and other small particles being carried along in the stream. That's the suspended load. And then lastly, there is the bed load. The bed load is stuff that's heavier than the suspended load, but still light enough to get pushed by the stream. It's stuff sort of bouncing along or rolling along the bottom of the stream. So this is larger things. So the dissolved load consists of minerals and elements that are carried by the stream in solution. Up to 20% of the stream load may be this dissolved portion. You can't see it. It's dissolved in the water. And it'll stay in that water until that water, I don't know, evaporates or something. Or I guess some chemical reaction could occur. But generally, the dissolved load will just stay in the water. The suspended load typically consists of fine to medium-grained discrete particles suspended in the flowing water. This is like silt and mud and maybe sandy particles if it's moving fast enough. And what's in the suspended load, the size of the particles that can be carried by the stream, depend on how fast the water is moving. The faster the water is moving, the bigger the particles it can contain. Which means if the water slows down for some reason, those larger particles will fall out. And this is why deposits from streams end up sorted. You all get particles of the same size because all the particles of the same size fall out when the stream slows down to below a certain speed. So the suspended load will change dramatically depending on the velocity of the flowing water. And then the bed load is larger grains that roll or bounce along the bottom of the channel. So here's a video showing bed load in short-lived streams in Alaska in the high tide zone. This is runoff in the high tide zone in Allerton, Alaska. And you can see the bed load here. So you're looking at the stuff that's bouncing along the bottom. There's little to no suspended load in this stream. Bouncing along the bottom here. That's the best. And you can see how the bigger, heavier rocks don't move, but the slightly smaller, lighter rocks do. Suspended right there for a moment. So let's talk about how streams erode the area around them. In the upstream portion of a stream, near where it starts, at its beginning, the stream has a long way down to go before it hits the body of water it's going to eventually empty out into. So it will erode down primarily. The primary direction that it erodes is down. It will cut a V-shaped valley into the earth. So in the upstream portion of the stream, flowing water will erode out a V-shaped stream valley. Eventually, it will reach the level, more or less the level of the body of water it's going to flow into. It can't erode any further down because there's no more, it's level with the water it's flowing into. It's not going to go for any further down. Most streams empty into the ocean, therefore sea level will be the lowest level to which they can erode. If you empty into a lake, streams that empty into a lake have the lake level as their lowest level possible. Now, the base level is the lower limit below which a given stream cannot erode. This is usually sea level or the lake level, or if you build a dam, you can change the base level by building a dam and creating a higher base level. The erosion from streams will go down until it hits base level, roughly, and then it'll still erode. Just the water is still flowing. It's still going to pick stuff up and move it. But it'll start, instead of eroding down, it'll erode to the sides. In the downstream portion of a stream, as the level begins to approach the stream's ultimate base level, the downward erosion slows and most of the stream's energy gets expended to the sides laterally as it erodes from side to side. And during flooding, the stream will overflow its bank and deposit sediments over a wide area. And over time, this will develop into a widened, flat valley that's called a floodplain. We're in one of those. So sediment will deposit. The stream will meander back and forth, widening this big flat valley. That valley will every once in a while fill up with sediment, and you'll get a floodplain. And so generally in the upstream portion, streams flow more or less straight as they wear down. And then at the downstream portion, they start to meander back and forth like you can see here and form a floodplain. There are, of course,
Wyoming is a mostly arid state, but many of our communities are actually built in low-lying areas adjacent to rivers and streams, known as floodplains. Floodplains are a natural part of a river structure, and during high flows, such as spring runoff, rivers will exceed the normal channel capacity and flow across the surrounding land, the floodplain. People have built in and near floodplains throughout history. In the past, rivers were important corridors for transportation and trade. Because they receive periodic high flows that often carry lots of sediment, floodplains have excellent soils and agriculture thrives in floodplains. In order to accommodate human uses, floodplains are some of the most altered ecosystems in Wyoming. The natural processes that make floodplains valuable to humans, attractive to wildlife, and highly productive also make them hard to manage. Channelizing streams and draining wetlands in the floodplain make these areas easier to develop, but many of the benefits, such as soil formation, are lost without periodic flooding. People living in floodplains should understand that no matter how these areas have been altered, they will still flood at some point in the future. The Federal Emergency Management Agency, FEMA, provides maps and resources for people living in floodplains. Your local extension office has additional resources to help you understand floodplains and also to assist with disaster management during floods. For the University of Wyoming Extension, I'm Milton Geiger, exploring the nature of Wyoming.
So one of the nice things about floodplains is that they steadily receive new sediments, and these periodically deposited within the floodplain. That makes floodplains some of the most fertile agricultural land in the world. Many of the places where agriculture first developed in the world were floodplains. Not all of them, but many of them. The famous ones in Europe and Asia were all floodplains. There are some exceptions in South America and such, but many of them are floodplains. And the rich soils lead these floodplains to become heavily populated because they've got a lot of agricultural land that can generate food for a lot of people. And despite their usually quiet appearance, floodplains are still prone to periodic flooding, causing significant damage to crops and structures. So streams will meander, bend back and forth. And particularly in the downstream portions, the stream will twist and turn, making loop-like bends called meanders. You usually see these in the downstream flat floodplain areas of a stream. There are exceptions to this, like the Colorado River has meanders that are dug into deep canyons. That's because the Colorado River was a meandering river, and then the whole area got lifted up and it started digging down instead of side to side and dug the deep Grand Canyon. But essentially, the stream will always take the path of least resistance. What will happen is that if there's any small bend in a stream, on the outside of any bend, the water will move slightly faster, causing more erosion. And on the inside, it'll move slightly slower, causing more deposition. And that will make the bend steadily larger and exaggerate this. And eventually, that bend can run into another bend, cutting off a section of stream. And that entire loop that gets cut off, that just remains, is called an oxbow lake. So here's a short video about the process by which oxbow lakes form. So, in any meander, faster flow on the outside of the bed, that causes the banks to erode. And on the inside, the flow of the river is slower, and materials will deposit. That'll change across the landscape, and eventually, when it's close enough, it'll cut off a section of the river. And if we make it to the meander that's just hanging around, that is an oxbow lake. It will eventually fly out into the depression in the floodplain. So here's an example of some stream meanders with oxbow lakes that you can see. Now, at the very end, when a stream hits the body of water it's flowing into, it slows down a ton. And that means it dumps out a huge amount of sediment. And streams erode and transport enormous quantity of material. And most of these sediments will eventually end up in the ocean where the stream ends. So for example, the Mississippi River carries 500 million tons of sediment into the Gulf of Mexico every year. 500 million tons of material is transported from the Mississippi River into the Gulf of Mexico every year. And most of this sediment, once it hits, say, the ocean, well, the stream's not moving fast anymore. It falls down. And they'll accumulate at the mouth of the stream as the stream's velocity significantly diminishes. And these will form what's called the stream's delta. It's called the delta because it's shaped like the Greek letter delta. It's vaguely triangular. So here is a video about how river deltas form and just general depositional features from streams.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem.
Hey, Houston. We are learning how the Earth is sculpted by water. And fancy term, depositional landforms. We're going to be learning about sediments and where they get deposited, and then what kind of a landform they create. The most simple one is called a sand or a gravel bar. And a sand or gravel bar, what do you think is going on? Is as a river deposits sediments, it can create a little bar, a sand bar. You'll see this out in Galveston. In many ways, Galveston and that whole area is a sandbar, is what it is. The second one is called a delta. Now, the deltas are named after the Greek symbol delta, and a delta is a triangle. I'm not sure if you can quite see this, but this takes the shape of a triangle. The river is meandering here, and then he snakes out here and here and here. Because ultimately what you're looking at right here is that these are sediments. So that maybe the mouth of the river was back here many, many, many years ago, and now it's depositing in the shape of a triangle, sort of spreading out. And how does a delta form? It forms actually in stages, right? The first stage is you get a nice, pretty channel, but then as that sediment deposits, then the channel, all this sediment gets deposited here, it shifts over here. And then, of course, it shifts over here because all that, it gets cut off because it fills in with sediment, and then we get a new snake. You see how it kind of is growing as time goes on because it deposits sediments. The sediments then create a little natural dam, and then the water says, oh, I got to find a new way, so it, boom, shoots out another way, and that's how a delta forms. And here's a cool picture. I mean, the Mississippi River, not far from where we're at, right? And this is the Mississippi River Delta, that down near New Orleans and all that kind of stuff right here. We've got the Mississippi River, and it's been this delta that's formed over many, many years. And even you've got this river, which is actually part of that whole Mississippi River system. Right now, this Mississippi River is extending way out here, and then we can start seeing the new delta. And notice you can see the sediment. This the white piece down here tends to be, well, not is, tends to be, it is filled with sediment, and it's like making the ocean shallower because you're depositing sediments, thousands of cubic feet, millions of cubic feet of sediment down out into the Gulf of Mexico. And now, part of this section goes to an interesting comment, is that how do we form a natural levee? A levee is like a dam, right? It's something that's going to cause it to happen, because as water flows during a flood, right? So you get a flood. What happens is the coarse sediments, the bigger pieces, they don't travel as far, and so they create they get deposited, the big pieces of rock, right, on the edges. And then when the water recedes, the flood goes down, then you've got a little natural levee. And then it floods again, you see, right? It floods again, and more coarse sediments. And you see how the natural levee, it's naturally. So this happens on a natural basis. After many floods, you're going to get sort of more like steeper banks of your river. So that's how a natural levee forms. And then lastly, we want to talk about something called an alluvial fan. I think this is a super cool picture. Is what you've got is you have this is a picture, right? This is in a river, but this is going to happen, and it creates this, you can see the fan-like appearance. Alluvial fans are kind of like a delta, but it happens when you're going to have super steep land followed by, so this is like a big mountain. So instead of like the Mississippi River that is flat where it's reaching the ocean, this is a big mountain, and then all the sediments get dumped in really, really fast because they're coming crazy fast from the super steep slope, and it makes an alluvial fan. Again, crazy short stuff. Streams, water, the world is sculpted and changed by water. We'll see you in class.
One of the ways we know that, for example, Mars had flowing water on it is we found alluvial fans there in craters. So water flowing down the edge of the crater, hitting the bottom of the crater, splaying out, leaving sediment. Another way that water can transport material is glaciers. So glaciers are large masses of ice that cover part of the Earth year-round. They consist of recrystallized snow and flow over the surface of the land under the influence of gravity. So even though glaciers may not look like they're moving, they're always flowing steadily down. And glaciers, what happens? Glaciers form when more snow falls than melts, basically. So you get enough snow piled up, it doesn't melt. And if you keep it up in certain places, just on average, more snow falls than melts. It'll build up. It'll start to compress the snow underneath it. forming it into solid ice, trapping air in it, which we could use to find out about the past and things. So much of North America was covered by glaciers over 10,000 years ago, including here. It's why it's so flat around here. There are still about 1,100 glaciers within the lower 48 states in mountainous regions. And about 3% of Alaska is covered by glaciers. And a glacier will form an area where over a number of consecutive years, more snow accumulates than melts. Basically, more snow is coming down than melts. So it has to be somewhere where it stays cold enough year round. So this is often, and enough snow falls. So this is often in the far north or south near the poles, or high in the mountains where it's cold. And if enough snow accumulates, it will compress, it gets squeezed, then it recrystallizes into solid ice. It gets squeezed by the weight of all the snow above it, and all the ice, the snow crystals bind together to form this glacial ice. And eventually the glacier will begin to flow downhill due to its own weight. It weighs enough that it flows downhill, and it can carry material with it as it flows. Now, most icebergs in the oceans are just big chunks that have broken off the edges of the continental ice sheets in Greenland or Antarctica. Because of these are the two massive continental ice sheets. And glaciers are changing due to increased air and ocean temperature, because now they're melting faster than they're accumulating snow, and that can be a real issue. So glaciers come in two main types. Continental glaciers cover most of Greenland and Antarctica. These are these big, massive ice sheets that cover huge areas of land. They used to cover much of North America 10,000 years ago or so, but they don't anymore. Because the earth warmed up since then. But there are also alpine glaciers, which we'll go through several types. Alpine glaciers are glaciers that form in mountain regions. One of these are cirque glaciers. These are much smaller and can be found in mountain regions located in hollow depressions that are relatively protected from the sun. They have shade. Most of the glaciers in the US are cirque glaciers. And as the glacier flows, it carves out a sort of round amphitheater-like depression called a cirque. And if the ice melts, these glacial depressions or cirques fill with water and are called cirque lakes. There are also valley glaciers, which are glaciers in valleys. Sometimes you have a cirque glacier feeding into a valley glacier. Valley glaciers occur when entire valleys get covered in glacial ice that flows down the valley. This is sort of the classic mountainous glacier that people think of. And the flow rates of glaciers depend on many factors and may vary from centimeters to meters per day. And eventually, at lower and warmer elevations, the glacial ice will melt. And if the rate of flow and the melting rate are equal, the glacier will appear to be standing still, but it's constantly having new glacier forming at the top and melting at the bottom. So here's a short video about, classifying glaciers and the difference between continental and alpine glaciers, basically.
Ancient glaciers have contributed to the formation of some of the most spectacular landforms on Earth, while modern examples provide data to help us figure out changes to our climate.
In today's video, we will start with the basics and discuss some of the most common features of two major types of glaciers.
A glacier is a long-lasting mass of slow-moving ice and snow. For a glacier to form, we need an environment where cold temperatures dominate for most of the year. Consequently, most glaciers are either found in polar regions or at high elevations on the continents.
We recognize two basic types of glaciers. Most of the world's ice is preserved in two massive ice sheets found in polar regions.
In contrast, High mountains on most continents are home to smaller alpine glaciers, also known as mountain or valley glaciers.
We'll begin with a closer look at ice sheets. Let's start with the obvious. Ice sheets are huge, extending for millions of square kilometers. Such large volumes of ice and snow can only accumulate and remain where temperatures are very low.
For example, Antarctica is the coldest place on Earth. Average annual temperatures in the high interior of the continent are about minus 57 degrees Celsius. Even areas along the coast rarely get above freezing during the year.
To cover such a large area, ice sheets must also be very thick. There are several kilometers of ice sitting on top of Greenland and Antarctica. Consequently, the ice sheet covers every landform, with the exception of some particularly tall mountains.
Glacial ice flows from the thick interior of the ice sheet to the thinner margins. You will have noticed that Antarctica is surrounded by ocean. A glacier that ends in the ocean may be known as a tidewater glacier.
There are many glaciers that flow off Antarctica and terminate in the ocean, where the ice can form floating ice shelves or break off to create icebergs.
Ice sheets contain ice formed recently, but they also have layers of ice that were formed up to hundreds of thousands of years ago. For example, some of the ice layers at the base of the Greenland ice sheet may be more than 100,000 years old.
The thicker ice on Antarctica extends even farther back in time. The European Project for Ice Coring in Antarctica has drilled the oldest existing ice core, which contains 800,000-year-old ice from a location in Antarctica known as Dome C.
Scientists can interpret the ice properties to figure out how temperature has fluctuated on Antarctica throughout that time. The record reveals a sequence of long cold periods separated by shorter warm episodes.
For more information about the relationship between the global distribution of ice sheets and variations in climate, watch our Ice Ages and Climate Cycles video.
Yeah, one of the nice things about glaciers.
Outside of polar
they
regions,
trap air.
alpine glaciers form at high altitudes in modern mountain ranges on every continent except for Australia.
Alpine or valley glaciers typically begin in a permanent snowfield at high elevations. For example, the Aletsch Glacier is the longest glacier in Europe and begins at an elevation of just under 4,000 meters in the Swiss Alps.
Let's take a closer look at some of the features of this glacier. More than 2,000 meters below the summit, temperatures are much warmer and cause the glacier to melt and supply water that then fills this substantial reservoir.
Traveling about 5 kilometers up the valley, we come to the end of the glacier where solid ice is buried under sediment at the glacier terminus. This sediment, a mix of large boulders, sand, and clay-sized particles, is largely derived from material breaking off or eroding from the valley walls.
We can follow this sediment a little further along where we notice these dark bands, known as medial moraine, that transport sediment along the glacier.
Notice the bathtub ring-like feature along the valley sides, indicating that the glacier used to be larger and thicker and occupy more of the valley.
Zooming in on the surface of the glacier, we can see cracks in the ice, known as crevasses, that form above locations where the base of the glacier moves over a step in the valley floor.
Continuing along, we see that the glacier we have been following is actually made up of ice from several smaller tributary glaciers.
These smaller glaciers flow out of steep-sided hollows known as cirques that form just below the ridge crest and serve as a supply source for the glacier. Notice that unlike the rest of the glacier, the cirques are snow-covered.
The overlying ridge is topped by a couple of pointed horn-shaped peaks characteristic of alpine glacial landforms.
Drawing back, we can see the full extent of the glacier from its beginnings in the high cirques to its terminus, 24 kilometers further down the valley.
Alpine glaciers are much shorter and thinner than ice sheets. They tend to move more slowly, and the age of the ice flowing through these glaciers is more likely to be measured in hundreds of years rather than hundreds of thousands.
Not all alpine glaciers are as impressive as the Aletsch Glacier. Some are much smaller, like these cirque glaciers in the Chugach Mountains of Alaska.
Some glaciers expand as they exit a valley to form wider Piedmont glaciers, like the Malaspina Glacier in Alaska.
We have 3 learning objectives for today's lesson. How confident are you that you can successfully respond to each objective?
Here's an image of a valley glacier with the medial moraines going through it. So as a glacier flows, it'll loosen up and carry away eroded rock material, much of which is eventually ground up. Though it's much slower than streams, glaciers are not as selective, and they're able to pick up huge boulders and gouge very deep troughs. And deep U-shaped valleys are typical of glacial erosion. So glaciers cause U-shaped valleys, streams cause V-shaped valleys. And glacial sediment doesn't get sorted. It all just flows with the glacier. So it's the deposits from glaciers, till the material that's been transported and deposited by glacial ice, are generally not well sorted or particularly layered. You just get a bunch of whatever. And the sides and ends of a glacier can form ridges of till called lateral and terminal moraines. And the end or terminal moraine marks the furthest point the glacier has advanced. And terminal moraines can be found as far south as Indiana, Ohio, and Long Island, New York, from the massive glacier ice sheets that used to cover North America. Yeah, and that's why it's so flat around here, because that whole area was basically straight flat by the glaciers. And so these are moraines. Lateral moraines are on the edges. Medial moraines are in the middle. They're strips of material being carried along. And then end moraines or terminal moraines are where the showing points where the glacier ended, and they drop. And so this is the last one, and then these are recessional moraines as it moves backwards. So these are end moraines, and the last one is called the terminal moraine. Now, wind erosion is an important factor in places that are dry, so in deserts. It is very slow, however. It's much slower than water movement. But it does very important processes, like, for example, the Amazon rainforest would not function the way it does without wind erosion, because particles are carried from the Sahara Desert across the Atlantic Ocean to help seed the rainfall in the Amazon rainforest, and also deposit certain minerals there. Deserts are defined by a lack of precipitation, but can be any temperature range. There are hot deserts, there are cold deserts. The definition is based on, the famous deserts we think about are hot deserts, but there are plenty of cold deserts as well. And the episodic thunderstorm can cause tremendous short-term erosion. So you get these flash floods that carry shocking amounts of material with them. And during most of the year, the wind is the prime erosional agent in the desert. And probably one of the most dramatic cases of wind erosion was the Dust Bowl of the 1930s, where, because the whole Great Plains area basically had all of its vegetation holding down topsoil removed and was all plowed, and then it got very dry, all that topsoil blew away. And that was the wind-blown topsoil. It was the Dust Bowl. And now another common form of erosion is just stuff falling down the hill, mass wasting. It's the general term for downslope movement of rock and soil just under the influence of gravity. Gravity tends to pull the material down, and friction tends to act to keep the material stationary. And the presence of water in the material will significantly affect the forces of both gravity and friction. And it's actually kind of complicated, because a little bit of water can actually increase the amount that particles stick to each other, so make it more stable. But in general, lots of water, the addition of water adds weight to the material and also generally reduces the friction between the particles. So in general, the addition of water promotes slope failure. The addition of any significant amount of water promotes slope failure. There's some very weird stuff going on with small amounts of water, but we don't need to worry about that. Basically, the surface tension of the water can help hold the particles together if there's just a little bit of water coating them. But if there's enough to fill all the gaps in between, that helps it fall down. That's why wet sand piles up better than dry sand, moist sand. So Mass wasting can be classified into either fast or slow. Fast or catastrophic mass wasting occurs in two basic forms. Landslides, which is when a large blocks of weathered material rapidly slide down a surface. So if large volumes of rock are involved in a landslide, it's called a rock slide. But this is just chunks of material rolling down a hill. And then mud flows. So the difference is that a landslide, just materials slides down the slope. A mud flow involves the rapid downslope movement of soil that's become unstable due to the absorption of large amounts of water. So it flows like a viscous liquid. So a landslide will just slide down and pile up. A mud flow will flow down and spread out because it's made of mud. So this is a mud flow. You can see this whole area absorbed a lot of water, flew, overwhelmed these large areas. One of the a very dangerous volcanic thing. There are volcanic mud flows. They're called lahars. They can be very dangerous because all the ash and dust created by the volcano can then get saturated with water and flow very quickly. There are also slow mass wasting events. So slump is the relatively slow down movement of an essentially unbroken block of overburden. This is where you have like a big chunk of material that just sort of slides down. They leave a curved depression in the slope, marking the detachment zone. Often that chunk of material, it doesn't break, it just sort of slides down the slope and maybe rotates. Then there's creep, which is the very slow, imperceptible particle by particle movement of debris down a slope, which causes things to bend over. You get weird shaped, J-shaped trees. It's too slow to see the movement because it's, tiny, tiny amounts. But the results of years of creep can be seen along slopes. And abundant vegetation and its root structure help deter all types of mass wasting because the roots help hold the soil together. So here is a video about the various types of mass movement or mass wasting.
Mass movement is the movement of surface material downhill due to gravity. The loose surface material is known as regolith. There are four main factors which influence mass movement. Gradient, the steepness of a slope. Water, this is generally in the form of rain, making the regolith heavier and more unstable. Human activity, such as the building of roads and railway lines which undercut a slope. And vegetation, the roots of trees help to bind the soil together to make it more stable. Soil creep is a very common form of mass movement and can be seen in the landscape all around us. Any second now. Still no? That's because soil creep is a very slow form of mass movement, often as slow as 1 to 2 centimeters per year. Similar in a way to the movement of tectonic plates, you cannot see the movement, but can see the impact of soil creep over time. Tree trunks bend and telegraph poles lean downwards. Fences may collapse and walls can have soil build up behind them before eventually bulging and collapsing. On grassy slopes, the soil may form at the steps known as terracets. As soil creep bends the lower trunk of a tree, it will begin to lean over. However, the trunk will then straighten as it continues to grow upwards. This is to maximize the amount of sunlight that the tree receives. Landslides occur when loose rock and soil move down steep slopes in upland areas. The removal of vegetation and the undercutting of slopes to build roads and railway lines can combine with heavy rainfall to lead to a landslide. A landslide scar is often left behind as the surface layer of soil and grassy vegetation can be removed. Like other fast forms of mass movement, landslides can cause significant damage and destruction to animal habitats, farmland, and human settlement. Mud flows are a very fast form of mass movement. They can occur in areas of high rainfall with steep slopes where vegetation has largely been removed, such as on farmland in the west of Ireland. Heavy rainfall can make the soil saturated and unstable, creating a fast-flowing river of mud that can flow freely and travel several kilometres downslope. Bog bursts are similar to mud flows, but occur in upland areas where peat is found. A lahar is a volcanic mudflow and generally can lead to more casualties in an area surrounding a volcano than lava. When volcanoes are active and erupting, they produce a tremendous amount of heat. If the summit of a volcano is snow-capped, the snow and ice will melt. This will mix with the volcanic ash and soil on the mountain to form a volcanic mudflow. The Nevada del Ruiz volcano in Colombia erupted in 1985, creating a lahar which moved downhill at over 80 kilometers per hour. Over 20,000 people were killed and 5,000 homes destroyed in the town of Armero, which lay at the base of the volcano.
So that is the process of mass movement, material flowing downhill. Let's talk about water. Water is essential for life and it's required to maintain our body function. About 55 to 60% of the human body is made of water. And early civilizations tend to flourish where water was abundant, often in river valleys, because lots of fertile soil means lots of plants growing that are often edible food. Modern societies are also keenly concerned about the distribution of fresh water. And the global water supply is constantly in flux, being redistributed throughout the earth. It evaporates, it comes down as precipitation, it flows out into the oceans, things like that. This process is known as the hydrologic cycle, the constant movement of water from large reservoirs, oceans and lakes, to the evaporation to the atmosphere via evaporation, then onto the land via precipitation, and eventually back into the sea via runoff. And a lot of this process we can readily see as things like clouds, rain, snow, lakes, and flowing rivers. And a significant portion of the precipitation will soak into the soil and bedrock and become part of the very slowly moving groundwater system, but essential. The groundwater system is very important. It's where a lot of people get their water from, for example. And this is the water cycle, the cycle of water from throughout. So all the water on Earth is constantly moving. Some of it's not moving very fast, but generally it's all moving.
The one factor that most dramatically sets Earth apart from other planets is water. Though the total supply of water has remained constant on this planet for millions of years, it never remains stationary. One of the most active Earth materials, water, is constantly moving. Its movement accounts for many of the landforms on our Earth's surface. Here in Iceland, fresh water erodes through rocks, slicing across the terrain on an ever downward journey to the Atlantic Ocean. But fresh water accounts for very little of the world's total water supply. Most of the Earth's water, more than 97%, is in the oceans. In fact, fact, almost 71% of the Earth's surface is covered by these salt waters. Most of the Earth's fresh water is stored in glaciers near the North and South poles. In warmer weather, some of the ice melts and the runoff returns fresh water to the ocean. Fresh water can also be found in lakes, streams, and water in the ground. The rest of the world's water supply can be found in clouds. The amount of water in the air is minute when compared to the amount of water on the Earth's surface. The clouds are formed from water evaporated from the Earth's surface and condensed as air cools. The water can then be released to fall back to Earth as precipitation. The most common form of precipitation is rain. We call this constant exchange of water between land, sea, and air the water cycle.
So the Earth's 1.25 times 10 to the 18 cubic meters of water is constantly moving. The vast majority of the Earth's water is salt water in the oceans. Most of the surface of the Earth is covered in ocean. That ocean is where most of the water is. So 97.4% of the water on Earth is in the oceans. And then there's a small amount, about 2.5% that is remaining that's not in the oceans. That's things like groundwater and surface water, which is about 0.8%, and ice, which is about 1.8%. So about 70% of the surface of the Earth is covered with water. 97.2% is ocean water. 2.15% is frozen in ice caps and glaciers, and only about 0.65% is found in lakes, streams, groundwater, and the atmosphere. And groundwater alone serves as the source of half of our drinking water and nearly half the water used for agriculture and industry. I mean, not so much around here because we have a big freshwater lake that we can get our drinking water from, but just in general, groundwater is the primary place that people get water. And the study and proper management of groundwater resources has become one of the key environmental issues facing the world, especially because things like agriculture and industry and things are using lots of it and depleting. You know, they're using more groundwater than deposits in the aquifers in question. And at the present time, human usage of groundwater is increasing each year, and it already exceeds the natural rate of recharge. And in most areas, the groundwater reserves took thousands of years to accumulate, but can be depleted in only a few years. That's a real issue. And in also many areas, groundwater gets polluted by human, industrial, and agricultural waste. And a big issue with this is that there's a lot of corporate use of groundwater that's really excessive. But let's talk about groundwater. So, the rock that makes up the ground, let me just check something. So the movement of groundwater through the rock that makes up the ground depends generally on the physical characteristics of soil and bedrock. And there's two properties that we talk about. Porosity is how much of soil or bedrock is made of empty space. The percentage of the soil, bedrock, or sediment's volume that's composed of pores. Now, how much holes does it have? So if you take a bunch of dirt, dry dirt, put it in a beaker, and pour let's say 1,000 milliliter beaker, and put 500 milliliters of dirt in there, and then you pour 500 milliliters of water in it, it's not going to fill up to 1,000 milliliters because there's a lot of empty space in that dirt. So it's the porosity of an underground reservoir that determines the material's capacity to store water. So porosity is how much room there is for water. And the other important physical property is permeability, which is how easy it is for water to flow. So porosity is a measure of how many holes there are. permeability is a measure of how well those holes are connected. And since we're out of time for today, I think I will stop there. So permeability is a measure of the material's ability to transmit fluids. So I'll stop there for today. I'll see you guys on Tuesday. Stop sharing.